This week we're focusing on light and telescopes, the primary way that astronomers learn about the universe through collecting light and analyzing it, primarily using telescopes. And we're going to zero in on 10 things that are really important to know about light as kind of a basis for a lot of what we're going to do going forward. So this is a lecture that you'll probably want to come back to and review as we do other things that relate back to one or more of these 10 things. All right, so the first thing is that light is an electromagnetic wave. It's essentially an oscillating electric and magnetic field, which by the principle of induction, one induces the other, which induces the other, and it propagates forward. The fact that it's a wave is really, really important. And so going forward, when we talk about light, you should think about wavelength. And so we're going to talk about light in terms of the wavelength and specify what wavelengths mean what as far as what we're looking at. In general, waves have a frequency and a wavelength and a speed, and they're all interrelated by the equation over here. So the variable c is the speed of the wave, how fast it's moving. The variable lambda, that's the Greek letter lambda, is the wavelength, so from crest to crest. Because it's an electromagnetic wave, it's like the peak of the electric fields or the peak of the magnetic fields. That's the wavelength. And then the frequency, so how fast the wave is oscillating up and down, how many times per second. And these are all related by this equation. So wavelength times frequency gives you speed. The speed of a light wave is always constant. We've used this number before, 3 times 10 to the 8th meters per second, or 186,000 miles per hour. And we're going to talk a little bit more about Einstein's theory of relativity later in the semester when we cover black holes. But for now, you can know that nothing can travel faster than light. It's an apparent law of nature that nothing can travel faster than light. And so that makes light very, very special. And certainly you'll come to understand that as we progress through different topics. All right, so just how we'll use that equation going forward. Because the speed, frequency, wavelength are all interrelated, when you know any two of them, you can calculate the third. And because the speed of light is constant, you always know that one. So that means, practically speaking, if you know wavelength, you can calculate frequency, and if you know frequency, you can calculate wavelength. So there's an example here, radio broadcast. A radio broadcast is an electromagnetic wave. It is light. It's light that we can't see, but it's light. And it's broadcast at 105 megahertz. A megahertz is 1,000,000 hertz. And the question is, what is the wavelength? We can rearrange the speed, wavelength, frequency equation, take speed, divide by frequency, and you get that the waves are about 2.86 meters. So this frequency wavelength, this frequency wave corresponds to a wavelength of about 3 meters. And as I said before, the wavelength of these waves is a very important thing to understand. And just get familiar with like what wavelength means what. And we will hopefully that will make a lot more sense as we use that idea. Second thing, light is also a particle of energy. So the history of studying light is very, very rich and deep. But for a long time, the basic question was, is light a stream of particles or is it a wave? You know, is it like a sound wave, a water wave, or is it more like the rain? And the theorists who were thinking about this would go back and forth. And ultimately, the reason they never came to an understanding before the last 100 years or so was because light is actually both. It's a particle of energy. It's a stream of particles of energy called photons. And those particles have wave-like properties. They're moving in a wave. So it was both. it's a particle and a wave, and both of those properties of light are critical to what we do. So what this means is that light has chunks of energy. So each photon carries a certain amount of energy, and that amount of energy is proportional to its frequency. And that's what this equation here is showing. Energy is a constant times the frequency, and this constant is known as Planck's constant, after Max Planck, who first proposed this idea. And it's a constant, so it has a very specific number, and that's the number right here. So let's take a look at how we use that. Let's consider two different photons, a blue photon and a gamma ray. Now, you don't need to know what a gamma ray is yet, but I'm giving you the frequencies of both. Frequency of the blue photon is this number. The frequency of the gamma ray photon is this number. Now, pay attention to the power of 10. This is 10 to the 20th, 10 to the 14th. So that's six different powers of 10. That means that the gamma ray is about a million times faster frequency. It's oscillating back and forth a million times faster than the blue photon. So how does their energy compare? Well, we can calculate the energy of the blue photon, Planck's constant times frequency. We get this number. Energy of the gamma ray, Planck's constant times frequency, we get this number. And to compare them, we look at one divided by the other, and it's 480,000. So about 500,000. So it's about 500,000 times the energy of the blue photon in the gamma photon. And so that's these things that I'm talking about so far are all interrelated. We're going to categorize light by wavelength. The wavelength is connected to the frequency, and the frequency essentially determines how much energy it carries, and that will have important applications for us. Okay, so where does light come from? Number 3, light is made by atoms. So light always comes from atoms. That's where it's generated, inside of atoms. And so we need to have a basic understanding of what an atom is. It has a nucleus, and I imagine this is review for a lot of you, most of you probably. But we need to just have a basic familiarity with the anatomy of an atom. It has a nucleus. Protons and neutrons are in the nucleus. The protons have positive charges, the neutrons are neutral, and then surrounding that is a cloud of electrons. The simplest of all these atoms is hydrogen, a single proton and a single electron. That's all there is to it. Most of the universe is made up of hydrogen. And when we get to study stars, we'll see that stars are giant balls of hydrogen gas. So how do they produce light? Well, the electrons have to obey very specific rules. They live in energy levels. And so it's very, very strange why they behave the way they do, but this is a rule of nature. They can only have certain amounts of energy that are particular to that atom. When they transition between levels, they're either absorbing an electron or giving up absorbing a photon or giving up a photon. And so the energy levels, we talk about high levels being high energy and low levels being low energy. So if it goes from a high energy level, so like the level 5 up here, and drops down to a low level, let's say all the way down to level 1, it's dropping levels, meaning it's dropping energy. The only way an electron can drop energy is if it gives off a photon. So we say it emits a photon. Conversely, if it's at a low level and wants to jump to a high level, the only way to do that is to absorb a photon. And so atoms produce light or absorb light, emit photons or absorb photons, and that's correlated with their changes in energy levels. The energies of the photons are exactly the same as the difference between the energy levels. Number 4. I should mention now, these are in no particular order. These are just 10 things that we need to familiarize ourselves with about light in not any particular order. But number 4 on my list is most light is invisible. We can't see it. And I've already hinted at this by mentioning radio and gamma rays. Those are things we can't see, but they're the same basic thing as the light that we can see, electromagnetic waves. And so we call all of the possible electromagnetic waves the electromagnetic spectrum, and then we think about it in these bands, these ranges of wavelengths. So let's look at the picture here. We have short wavelengths on the left, long wavelengths on the right. Short wavelengths are large energy. So high energy to low energy, short wavelength to long wavelength. The wavelengths we will think of in terms of nanometers typically. That's what the NM stands for, nanometers, a billionth of a meter. And that's because the visible light range is in the hundreds of nanometers. And so when we think about light, we'll often use the units of nanometers. So very, very small, very, very large. And then the band names. So gamma rays are the smallest. The smallest possible wavelength light is gamma rays, then X-rays, ultraviolet, the visible range, infrared, microwaves, radio waves. And then if you're talking about them in terms of their frequency, it just goes the other way. So this is high frequency, low frequency, long wavelength, short wavelength, long wavelength. Now, that visible range right here, this is the only portion that we can see. And it ranges from, it's not listed on here, but it ranges from about 400 to 700 nanometers in size. Only that tiny range. Everything else is invisible to us, at least to our eyes. But it will be extremely useful for us to look for light that is invisible. Now, I added this diagram in here as well. So this is the same, we're on the same number in our list, number 4. And I added this diagram in because it illustrates what's happening to the light from the sun. Sunlight contains a broad range from gamma all the way up to radio waves, but it doesn't make it down to the earth. And so if you ask yourself, why can we only see the small range of light, this visible range? That's because that's the center of the spectrum that we get from the sun. So most of the light that hits the ground is visible light. And so we have evolved to see visible light. The shorter wavelengths, they all get absorbed in the atmosphere. So the bars here indicate how deep they penetrate before they get absorbed. Didn't mean to drag that. And so you can see some of the long wavelengths penetrate better, but there's actually less energy in this part of the spectrum. So we didn't evolve to see radio waves, but the radio waves do make their way down. But because they're able to penetrate through the atmosphere from the sun, we can actually use that to our advantage and communicate with each other on Earth by radio waves. Radio waves pass through the atmosphere pretty well. So our radio signals are radio waves. Okay, but the bulk of the light from the sun, the majority of the light from the sun, is in this visible range, and it gets less intense as you go to either side of the optical, what they call here the optical window. This shows a similar thing here. It's the absorbance of the atmosphere and the sunlight, just looking at it in a slightly different way, how you get what light gets down to the earth. It's just in reverse. So now the radio side is over here and the gamma ray side is over here. But I added this one in because it shows you how we have found uses for all the different bands in the electromagnetic spectrum. So radio waves, we have AM and FM radios, our Wi-Fi signals and cell phones and microwave ovens, they're in the radio to microwave range. Our human bodies, we'll talk more about this in a bit, but our human bodies radiate part of the electromagnetic spectrum in the infrared. Our remotes use infrared. Ultraviolet rays are dangerous to us, so we wear sunscreen to prevent sunburn. X-rays are used in medicine, and gamma rays are produced in nuclear power plants. All right, number 5. All matter emits light. I should put an asterisk here. We're going to talk about dark matter, which is matter, and we'll get into what it is, but it doesn't emit any light and doesn't interact anyway. But everything, so I should say everything besides dark matter emits light. And what's important for us is that every element or molecule in the universe has a unique spectrum. So hydrogen always looks the same. So this is the hydrogen emission spectrum. It always emits a really bright red light here and a couple of really bright blue lights and violet lights. Helium has this pattern, nitrogen this pattern, and so on. They're all unique. And so this is a way for astronomers to recognize the elements. If you have, let's say, argon gas in the universe, and it's heated up and it's emitting light, then you're going to see this pattern of light. And so here's a periodic table to sort of hammer home this idea. This is a periodic table with no element names, but just their spectra shown, and indicating that every element is different. And the same would be true for molecules. So I don't have any molecules on this slide, but molecules would have their own unique emission spectrum. And so astronomers can identify elements and molecules whenever they can get the light to be recorded. Now, on the previous slide, they were all emission spectra. I wanted to just also talk about continuous spectra. So this is a continuous spectrum, meaning that there's all the colors present. So if all the colors are present, then we call that a continuous spectrum. And then if there's only specific colors showing, and we think of them as spectral lines, then we call that an emission spectrum. Now, related to point 5 is that all matter also absorbs light. So that's number 6. All matter absorbs light. It emits and it absorbs. And so there are things called absorption spectrum. And that has to be a special arrangement. When you have, let's say, a cloud of gas and a source of a continuous spectrum, when that light passes through, instead of the light getting emitted by the cloud of gas, it will absorb the same colors that it would also emit. And so in this scenario, you get a pattern that looks like this, which is almost a continuous spectrum, but it's got specific lines missing. Those lines would be the emission spectrum. But the gas isn't emitting light, it's just absorbing it as it's passing through. Because remember, atoms can do both. The electrons in those atoms can jump up a level when it absorbs or drop a level when it emits. If the gas is cool and those atoms are all out, so the electrons are all in low levels, when continuous light passes through, those electrons are going to readily absorb the light and jump up to higher levels. On the other hand, if you have a cloud of gas and it's heated up for some reason, those electrons are going to be initially at some higher level because they're heated up, and then they'll randomly jump down in levels and emit light, shine that heat away, essentially. And so if you look at the picture over here, you can see that the emission and absorption spectra all line up. They're sort of mirror images or inverse images of one another. Absorption spectra are almost continuous with some dark lines, and emission spectra are all dark except for a few bright lines. Now, we're going to be mostly interested in stars going forward, and stars have absorption spectra. This is the visible portion of the sun's spectrum, all mapped out sort of in a grid here. So starting from the violet, and you go left to right, read it left to right, just like you were reading a book, and you eventually get into the red. and there are bunches of lines missing. Those lines are telling us a story. They're telling us what the light has passed through in the sun's atmosphere as it left the sun. So we'll get into how the sun produces light in a couple weeks. For now, the sun produces a continuous spectrum, but that continuous spectrum has to pass through the sun's atmosphere. The sun's atmosphere contains lots of different atoms and molecules. All of them are working together to produce this absorption spectrum. And so astronomers can determine what lines here correspond to what different elements. And we'll see that in more detail when we look at the sun in more detail. All right, number 7. A black body is an object that can absorb and emit all wavelengths. So this one is basically a definition of what type of thing produces a continuous spectrum. And I bring it up because the term is sort of counterintuitive. You're probably familiar with the idea that if it's a hot day, you'll wear a white t-shirt instead of a black t-shirt, right? Maybe if it's a cool day, you'd go the other way. And that's because the black t-shirt is going to absorb all the sunlight that hits it, and the white t-shirt's going to reflect it. So they sort of do opposite things to the sunlight. Well, that means they're sort of, the colors black and white are sort of intimately related to one another. And in astronomy, a black body is an object that can absorb all the wavelengths of light, and then also when it's heated up, emit all those wavelengths of light. So it's a little bit counterintuitive. There probably should be a better term for it. Maybe just call it a continuous emitter or continuous spectrum object or something like that. But the term is a black body. And the spectrum of a black body is a continuous spectrum with a peak somewhere in the middle. And where that peak falls depends on the temperature. So I'll explain this graph in the next slide. That radiation of light, so I've already said this, but number 8, the radiation of light depends on temperature. And so if we have an object that's radiating light across the full electromagnetic spectrum, it's going to have a peak somewhere at some wavelength. And so what's on the diagram here are this intensity of light at each different wavelength, going from, the smallest possible wavelength up to long wavelengths. And each of the curves is a different temperature object. Now you can think of them as stars, because stars are essentially black body emitters. They do produce absorption spectrums, but those are like an adjustment, a correction, small correction to what it's doing. And so think of this as like a blue star, and this is like a orangish red star. Well, the blue star has a peak over here, and it's obviously taller. That's because it's hotter. Hotter stars have a peak at a smaller wavelength. Now that should make sense because lower wavelength means more energy. And this might seem all very complicated and there's a lot of things, but I'm laying all these things down here, and hopefully we'll come back, or you'll come back to these as the ideas become important to us. So if it's all seeming a little bit foggy right now, don't worry too much about it. It'll become more clear as you use these things, and the ideas will get more familiar to you. Small wavelength, more energy, and that means it's going to be emitting more intensity of light. So blue stars are hotter. On the other hand, reddish, orangish stars, they're going to be cooler and emit less intensity of sunlight. And their peak is going to be at a longer wavelength because they're emitting more red light than blue light. They'll look orangish, but actually their peak might be completely different, right? So the peak of this is not actually even in visible light. It's in infrared probably. There is a specific equation that tells you where this peak would be in relation to the temperature, and it's called Wien's law. So Wien's law is written right here. The way that it's written, the wavelength you'll get by the calculation is in nanometers, and the temperature needs to go in units of Kelvin. So can't use our more familiar Fahrenheit or Celsius. You have to put it in Kelvin, and then you'll get the wavelength in nanometers. And we'll see that in the next slide, how that works out. So I've listed a bunch of different objects and their temperatures, and then plug that into the equation to see how it works out. So empty space. Empty space is 2.7 Kelvin. So because it has a temperature, that means it's emitting light. So that's an important fact to remember. Anything with a temperature now is going to emit light. Empty space is not really totally empty. So maybe I should have put it in quotes, but what we think of as empty space has a temperature of about 2.7 Kelvin. Plug it into Wien's law, and you get 1.1 million nanometers, and that puts it in the microwave region, meaning that empty space is actually filled with microwave radiation. Pluto is 44 Kelvin. Plug that in, it's 68,000 nanometers. It's emitting infrared light. Go to the human body, 310 Kelvin. Its wavelength is 9,700 nanometers, still in the infrared. So the planet, or the former planet, the dwarf planet Pluto, and the human body are both emitting infrared light. And so they'd be brightest if you're looking at them with an infrared telescope. Now we're going to jump up in temperature to the surface of the sun, 5,778 Kelvin. That has a wavelength of 520 nanometers, which puts it right in the center of the visible spectrum. If you remember a few slides ago, I said that visible spectrum is about 400 to 700. So the surface of the sun is right in the middle of that range. That's where its peak is. But the sun is not a particularly hot star. If we go to a much hotter star, Sirius, which is one of the brighter stars in our winter sky, I think it's the brightest star in the winter sky, aside from the sun, is 9,940 Kelvin, corresponding to a wavelength of 302 nanometers, meaning its peak is actually in the ultraviolet. On to number 9. Light can refract and disperse when transmitting through a material. So I've mentioned how light gets absorbed by the atmosphere. Different bands get absorbed differently in the atmosphere. Well, another thing that happens when light passes through a material is that it changes direction, and we call that refraction. And it's actually the principle by which prisms work. The light enters the prism and spreads out, and the colors spread out into slightly different angles, and so it ends up in a rainbow. And it's also how rainbows work, because the light is passing through water droplets and refracting and getting spread out into its component colors. And I put this on here because it's great that we know all this about light, but we need a way to take that light and dissect it. And the fact that light can be spread into its component colors means that it can be analyzed color by color, wavelength by wavelength. And so these principles here are essential to analyzing the light that we get from stars. The fact that you can spread a beam of light into its component colors is absolutely essential. And then number 10, the last on our list of things that you need to know, is that motion relative to a source leads to the Doppler effect. And by source, I mean a source of light. So if a star is moving towards us or moving away from us, we get this effect known as the Doppler effect. The wavelengths get shifted slightly. So the diagram here is showing absorption spectra for a particular element. I think it might be hydrogen. It looks to me like hydrogen's got the bright red line and then some blue lines. So suppose this is an absorption spectrum from hydrogen gas. Well, if that source was stationary, it would look like this. If it's moving towards us, we say it is blue shifted. And what will happen is all the wavelengths will get a little bit smaller. So this line shifts over here, this line shifts over here, and so this is blue shifted. Everything's shifted a little bit towards the blue end. If the source is moving away from us, these lines all get shifted a little bit to the right towards the red side of the spectrum, and we call that red shifted. That will be an important idea for us, especially when we get to thinking about galaxies. So you'll need to hold on to this one for a while before we come back to the Doppler effect. But when we get to galaxies, we'll learn a very important fact about them is that they are mostly redshifted. And we can calculate how fast they're moving away from us by how much they are redshifted using this Doppler effect equation here. So there's a wavelength shift, which we call delta lambda. The rest wavelength is the wavelength it would have if it was stationary, and that's related to the speed of the source divided by the speed of light. And we'll finish up with one example of that equation. So how fast must a blue star be receding from us to appear red? Well, we can plug into that equation. We're going to find this ratio, V over C. So one wavelength minus the other, that's your shift in wavelength from 650, or not from 650, from 475 to 650. So it's this change, divide by its original, it's unshifted, 475, and we get a value of 0.368. So that means V divided by C is 0.368. Or another way of saying this is that the speed of the star must be 36.8% of the speed of light. So that's how fast it would be moving. In this case, it goes from being blue to appear red, so it's red shifted. So it's moving away from us at 36.8% of the speed of light. All right, so those are the 10 things. We will come back to them at various points and build our understanding of the sun and of stars and of galaxies off of what we can learn about light. And in the next video, we'll kind of continue this idea, but focus more on the technological aspects of telescopes. How do telescopes take in the light and then do something with it that can be useful?